Welcome, everyone. Thank you for tuning in. I am very pleased to welcome you all to our now seventh webinar in the Rain Enhancement Hub series hosted by the National Center of Meteorology and organized by the UAE Research Program for Rain Enhancement Science. My name is Sarah Al-Amri. I am a program officer for the UAE REP and I'll be moderating today's session. During the course of our last 6 webinars, we've been breaking down the complex processes involved in rain enhancement research and discussing emerging challenges and the latest developments in the field. Today, we will be shining the light on the interconnectivity of rain enhancement science and the marine side of things. Gulf waters and what lives in them are strongly affected by meteorological phenomena such as the relationship between Shamal winds, coral bleaching, and ocean circulation. Joining me today to learn about the UAE marine environment as revealed by the Axis's research is Dr. Francisco Paparella, a Global Associate Professor of Mathematics at New York University in Abu Dhabi. Dr. Paparella holds a laureate degree in physics from University of Torino and a PhD in geophysics from University of Genova. He held postdoctoral positions at Woods Hole Oceanographic Institution at the University of California in San Diego. His research focuses on geophysical fluid dynamics, where he gave seminal contributions in the field of horizontal convection and doubly diffusive convection. More recently, his interests have expanded to include modeling of biological and ecological processes relevant for Earth system science. We are very pleased to have him present his work for us today. Audience, please go ahead and type in your questions at any time during the webinar in the chat box below. We'll be sure to address your questions during the Q&A session after the presentation. Over to you now, Dr. Paparella.
Dear Sarah, thank you very much. Thanks for the nice presentation and a warm thanks to the NCM for having me today and to the public for listening. So I would like to share my presentation. And today I'm going to talk about the marine science that is being undertaken by the Arabian Center for Climate and Environmental Sciences, which is a newly established center at New York University Abu Dhabi, which I have the honor of being the director of. And the main goal of the Center for Climate and Environmental Sciences is that to develop an environmental observation network for the UAE. This is really the primary goal, because it turns out that, believe it or not, the Gulf region, from an environmental and climate point of view, is severely understudied. And therefore, any other activity, any other scientific activity that we want to do in this sector will first need data. And then once we have data, we can try to synergistically integrate this data with modeling. We are a very strong modeling group and with laboratory activities, including genetics and genomics. And this will allow us to develop fundamentally new approaches for environmental and climate science at the regional level, which I believe is really the frontier of climate science. And then, last but not least, foster collaboration between government entities and promote capacity building in the environmental sector. In particular, we are very open to collaboration with all the government entities whose activities overlap with our scientific interests. Just to give you an idea of what we're trying to do data-wise, this map shows a number of dark spots. These are places where we have underwater data loggers that are sitting there monitoring the environment, taking data of various kinds, both biological and physical. And every month and a half, 2 months, our technicians go there, change the battery up, download the data, and do maintenance. These triangles instead are the places where every month we take data, profile, vertical data from surface to the bottom with a boat. We follow this transect, and very soon, in a month or so, we're going to deploy an oceanographical monitoring buoy at the position of the yellow flag. And this is our marine network, which is being constantly expanded. Next year, for example, we will have another monitoring buoy. I will cut this short. I could talk for hours about what we are doing in terms of taking measurements, but let me just summarize very quickly what I would like to talk about today. I will touch about coral bleaching, hypoxia, and desalination. And these apparently are three completely unrelated things, but in fact, there is a common thread. And the common thread is that meteorological phenomena, and therefore on longer timescales, climate and climate trends, marine physical oceanographical processes and biological processes, all these three aspects interact together in a very strong and sometimes unexpected way. So let's begin with coral bleaching. As you may have heard, if the temperature in the water gets too high, the corals first lose their color. That actually is because some symbiotic algae simply leave the coral, leave the surface of the coral polyps and start swimming along. And that is what produces the bleaching of the corals. And if this bleaching persists for too long, for several days or weeks, then the coral dies. The green line in this graph shows a record that was started actually by Professor John Burt well before Access was created. And this is a temperature record at the bottom of the sea on Sadia Reef, which is a reef just in front of the island that hosts our university. The blue line is instead the simulated, is the output of a model. Is a water column model that includes a number of processes, and one of the outputs is the bottom temperature. Okay, so we have a little bit of a cold bias in the winter, but in the summer we do a good job of reproducing the data. So why is this useful? Because when we have a model, we can use this model as a crystal ball and ask questions that we couldn't otherwise answer just by looking at the real world. We can play what-if scenarios, for example, with the model. And okay, so just to give you an idea, this model takes into account a large number of phenomena. I summarize some of them in this slide. One is wind, evaporation. There is, of course, solar radiation, the air temperature, the mixing due to tides, turbulence also due to the wind. And it has parameters imposed at the top of the water column that are essentially meteorological data: wind speed, solar radiation, as I said, pressure, cloudiness, and uses all this data to solve equations that describe the physical processes in the water column. In this way, we can do some hypothetical scenario. So in this slide, what we did is we repeat the same July day for 40 times. It's very abstract. And all that we change, we only change one parameter, which is wind speed. If we have a wind speed of 2 meters per second, this is the blue line on top, we have, of course, the daily cycle. These wiggles are the daily cycle in temperature, but we have temperatures of the order above 36 degrees. This kind of temperature would be deadly for any coral. If the wind is at 4 meters per second, then we would have the orange curve, which is at a level which is a bit hot, but still tolerable for most corals, 34.5 degrees. And then if the wind is at 8 meters per second, then we have a very cool situation at little bit just above 32 degrees. And corals would be very happy in the summer at that temperature. And finally, the red curve shows a situation where the wind is at 4 meters per second, but there is a burst of 5 days where the wind is consecutively at 8 meters per second. And you see a very sharp cooling, which only slowly recovers to the original temperature. So this immediately tells us that wind is a very important factor in determining the temperature at the bottom of the water column. And we'll see why in a second. So These instead are both model data and observed data referring to a realistic situation. So this is not an abstract situation anymore. On the left, you see 2013, and on the right, you see 2017. The daily observed temperatures are the green line, and the daily simulated temperature are the blue line. They're not perfectly coincident, but they're close enough. And the wind speed, the observed wind speed, is the red line. It's absolutely clear that the big burst of Shamal wind in the middle of the summer of 2013 produced a sudden cooling in the water, both in the model and in the simulation. In fact, I would say that the inaccuracies in our knowledge of the wind speed are probably the main cause between the difference between the simulated and the observed data. This wind speed really come from the ERAFI reanalysis. They are not in situ observations. So they are assimilated observations and they have some uncertainty, some probably relatively large uncertainty. But nevertheless, this is more than enough to show that in 2017, instead, when there was no big Shamal event during the summer, the entire summer was dominated just by the daily breezes, relatively weak. The temperatures at the bottom of the water column kept increasing throughout the first half of August and reached extremely high temperatures, almost 36 degrees. And in fact, in 2017, we had massive coral bleaching. Now, the bottom panels, and this is the interesting part, show a breakdown of the energy balance. So how many watts per square meter we had the water column exchanges with the atmosphere. And there are several processes that exchange energy at the surface of the sea. One is what we call the sensible heat. The sensible heat flux is simply the temperature that goes from the atmosphere into the water when the air is warmer than the water, or from the water to the atmosphere when the water is warmer than the air, just by contact, by conduction. And this is the red line, which is fluctuating around zero. It's really a negligible amount. Then we have infrared cooling. Of course, if the water is warm, it will emit infrared radiation. We cannot see it, but it's there, and it's a substantial amount of energy that just goes away. And this is the blue line. It's about 50 watts per square meter. But the greatest cooling factor is what is called the latent heat flux. And the latent heat flux is the heat that gets lost, that goes away from the water through evaporation. And this is the green curve, which in fact is extremely affected by wind. If there is a strong wind, obviously we have a strong evaporation, everything else being the same. And so even with a breeze, in a breeze regime, we have almost 200 watts per square meter of cooling just through latent heat, just through evaporation. But when there is the Shamal event and the wind reaches 9 meters per second on a daily average, we peak at 400 watts per square meter of cooling. And this is quite a remarkable number because that is directly comparable, for example, to the amount of cooling power that is installed in the AC apparatus for a mall. If you just in August, if you walk into one of the shopping malls, the AC will be uptaking about 300-400 watts per square meter in order to maintain a comfortable temperature in the wall. Here we can say that for the Gulf, the AC apparatus is the Shamal wind. So when there is Shamal in the summer, the corals have a comfortable environment. When Shamal is lacking, then the temperature may become dangerously high. And of course, this immediately begs the question on what is going to happen in the future. Now, we really don't know, but just this slide is a bit messy, but just look at the orange line. The orange line is the average wind speed over the years from 1980s to 2020. We do see a slight decrease in wind speed. So there seems to be, so far in the last 40 years, a slight but still statistically significant downward trend in wind speed. Is this going to persist into until the 20th, at the end of the 21st century? We don't know. Maybe this is just multi-decadal variability. Is definitely a topic that would deserve further investigations. Now let's move to oxygen. And this was really unexpected. We found that at the bottom of the water column, this is Dabia, these are data in Dabia Reef, which is not that far from the Saadiyat Reef, very similar. At the bottom of a relatively shallow water column, just a few meters deep, it is possible to observe hypoxic events. As you may know, just about every complex life form needs to breathe oxygen. And the world oceans actually do have oxygen dissolved in the water. And this comes from the atmosphere through mixing processes, but is also produced by photosynthetic organisms, which release oxygen in the water. So in the water column of your typical UAE reef, you will have a daily cycle of oxygen concentration, because during the day, both phytoplankton dispersed throughout the water column and corals at the bottom of the water column will produce oxygen. And of course, it's a matter of estimating how much of oxygen is produced with respect to the oxygen that will seep through the surface of the water column. So these are measurements. Again, this is a relatively complicated graph. Bear with me and follow this. We had two sensors, one at the mid-water, roughly in the middle of the water column, and the other at the very bottom in the coral frame, in the reef frame. The thin blue line shows hourly oxygen data, and this data clearly show daily oscillations. During the day, there is a lot of oxygen, plenty of oxygen, and during the night, there is no photosynthesis, and the oxygen goes down because you still have respiration from everything which is alive in the water, but you don't have photosynthesis anymore. The orange and the dark blue line are just smoothing averages of this data, and the green lines are the oxygen level that you would expect, given the temperature of the water, if there was no life in that water. So just the equilibrium oxygen level with the atmosphere. Now, what is in the black lines then are the mark the maximum and minima of every day. The horizontal black dashed lines are instead the hypoxia threshold. Every time that the thin blue line goes below the dashed line, then there isn't enough oxygen to sustain in a proper way life in the water. If this persists for too long, we would start to see mass mortality. If that lasts only a few hours, then of course the ecosystem will suffer as a whole, but nothing terrible will happen. So it's really a matter of the time extent of these hypoxia periods. There are a few things to observe. One is that hypoxia occurs at night. It always occurs at night, in the second part of the night, just before the morning, just before photosynthesis starts again. And the other important thing is that hypoxia is much more severe at the bottom. At the bottom of the water column, there is more hypoxic event and more intense than in the midwater. And this is recast, and these data are recast and summarized in these panels. These are just the daily cycles. So The blue line is the typical daily cycle of oxygen when there is no hypoxia. And at the bottom and in the mid-water, so the left panel is the bottom, the middle panel is the mid-water. And the green lines instead are the typical daily cycle in the days in which there is hypoxia. And you have the minimum oxygen that typically occurs at 3 a.m. at the bottom of the water column. And then the differences are shown in the right panel. And the dots show the hours in which the hypoxic days and the non-hypoxic days are significantly, statistically, show us a statistically significant difference. So how did we try to investigate this? Again, through models. And okay, don't be intimidated by this math. This is, in fact, a very simple model. We reutilized our water column model in order to compute the turbulent diffusion coefficient, this K that appears here in the water column. And with this turbulent diffusion coefficient, we describe how the oxygen moves around in the water column. And we have a production term from the phytoplankton. We have at the top of the water column a flux, the oxygen that comes from the atmosphere, or in the case if phytoplankton is super productive and there is more oxygen in the water than in the atmosphere, this would show the oxygen that goes from the water up into the atmosphere. And at the bottom, we have two terms. There is a production term due to the corals, and there is a consumption term due to anything that breathes into the sediment of the reef. And so our basic hypothesis is that what really is using up all the oxygen in the water is something that is in the sediment, is a microbial life that lives in the sediment all around the reef. And in order to test this hypothesis, we did some scenarios. Now at the bottom, we have on the left panel, we have the observation, and on the right panel, we have the difference between the observed oxygen levels at the bottom and mid-water. And in the A, B, and C panels, several models with several hypotheses. So in the A panel, we put only photosynthesis in the water column. We don't have corals, but only phytoplankton. In B, we only have corals, but no phytoplankton. And in C, we have both. And by looking at the differences, the most realistic result is, in fact, the case in which both corals and phytoplankton in almost equal parts contribute to create oxygen during the day. But of course, there is this breathing that during the night eliminates most of this oxygen. And in this way, we can actually estimate the fluxes of oxygen throughout a season or during a few days. So in the big panel, we see the oxygen fluxes, daily oxygen fluxes produced by phytoplankton in blue, by the corals in orange, and the oxygen fluxes that come from the atmosphere in green. Now, curiously, the green part is almost negligible with respect to the other two parts. And in red, we have the respiration. And then in the small inset, we have the hourly data. It may be interesting to look at the green and the black curves. They are both the atmospheric fluxes. The green curve is the one that comes from the model, and the black curve is the one that is inferred from the observations. They match fairly well. And again, they are, except then in the middle of the day, they are, except then when there is a strong wind that mixes up the water, they are essentially negligible with respect to the fluxes produced by plankton and the corals. Now, more of the same, but in the Central Gulf. I'll try to be quick here. Observations carried out by teams from Qatar University have shown that at the bottom of the Gulf in the central part, below 50 meters, there is hypoxia. And we have created a ocean circulation model. This time is not a water column model, is a very highly realistic ROMS model of the general circulation of the Gulf that reproduces these things. And in particular, we ran the model from 1980s to 2010. And the model shows us that the minimum concentration, this is the top row, the minimum concentration, the region of the minimum concentration, the minimum concentration is decreasing. The duration of these hypoxic events that occur in the middle of the summer is increasing. The number of the likelihood that an hypoxic event occurs in any given year also is increasing. And the first occurrence is also coming earlier and earlier during the year. In fact, here in panel A, you can see that the area affected by hypoxia every year has an increasing trend, which is statistically significant, and it's a bit worrying. Now, I won't discuss too much in detail the other panels. All that these other panels, the purpose of these other panels is to make hypotheses on what may be the cause of this hypoxia. And I will just give you the end results of something that was a very long investigation, whose merit is really that of my colleague, Zouair Lakar. It turns out that wind, yes, wind again, plays a role in determining the fluxes of water at the surface of the Hormuz Strait. This water that enters the Hormuz Strait from the Indian Ocean and goes into the Gulf is a nutrient-rich water, because the Arabian Sea is a nutrient-rich sea, more nutrient-rich than the Gulf. So if the wind slacks, there is an increased flux through Hormuz, and this increased flux through Hormuz, once this water is mixed with the rest of the water of the Gulf and goes into the bottom, essentially produces a fertilization of the algae present in the Gulf. And this increased biological activity produces an increased respiration, and this in turn uses up more oxygen and produces hypoxia. So again, it seems that a biological phenomenon is ultimately regulated by a meteorological phenomenon. And finally, and this is really the last topic I'm going to touch, let's talk about desalination. You probably all know that all the water that is being used by the Arab countries in the Gulf, nearly all, comes from desalination plants. And the amount of desalinated freshwater production today is staggering. Every day, all around the Gulf, is produced 22 millions of cubic meters of fresh water. But if you just count the plants that are planned or already in construction, by 2030, this number will increase to 40 millions of cubic meters per day. And after 2050, the estimates are around 80 millions of cubic meters per day. Therefore, by the end of the century, the number of cubic meters per day of freshwater production may very likely exceed 100. So is this big or is this small with respect to the Gulf? In particular, the question really is, for every liter of fresh water that you get out of the Gulf water, you are leaving behind something like 40 grams of salt. And this salt remains in the water and therefore contributes in increasing the salinity of the Gulf. Are we upsetting the salinity balance of the Gulf? If the Gulf becomes too salty, all the ecosystems will be upset. And if the salinity increases too much, this is not just being upset, they may be destroyed. So the question is relevant. And therefore, we need to look at a meaningful comparison term. And this comparison term is the net evaporation. How much water and therefore fresh water, evaporates out of the Gulf just naturally because of the action of the sun and the wind. And this is the answer. The red line shows the net evaporation average over 40 years every month. You have a minimum in the spring, a maximum in the fall, but this oscillates around an average of 1,000 millions of cubic meters per day. So this means that today we are already, the freshwater production through desalination is 2% of net evaporation, but by the end of the century, it will reach 10%. And that doesn't sound like a lot, but if you think about climate change, the global climate change that we are experiencing is an imbalance in solar radiation of 0.1%. So an imbalance of 0.1% in solar energy, the energy goes out minus the energy goes in, is enough to produce the climate change that we are experiencing. So here instead we are talking about a salinity imbalance, not energy, salinity imbalance of potentially 10%. So there is something to be investigated. And in order to investigate this, we used a very simple model. I won't go into the details, but here the Gulf is modeled like just a series of boxes that exchange water from each other. And the boxes that are exposed to the atmosphere are subject to the effect of the air temperature, to the evaporation, and all these boxes then eventually are in connection with the Indian Ocean. And this is my last slide. It's very complicated, but let's just focus to panel A. This shows on the horizontal axis, we have the amount of freshwater production. So today we are at 22. In 2030, we will be at 40. In 2050, we will be at 80. The dark red line is what we expect to see. And all the other lines are different scenarios. Some of these are extremely unlikely to occur. But in any case, in all of these scenarios, the increase in salinity is limited to 1 PSU. PSUs are units of measurement for salinity. The water in the Gulf is roughly at 40 PSU. It ranges between 38.5 and 44 PSUs, depending on the season and the place. So this increase is not particularly worrying. In fact, it's not worrying at all. And the main effect is not that much the freshwater production through desalination, but are the other effects that are in the model due to climate change. And why is it so? So the reason why the salinity does not accumulate is because there is a feedback through Hormuz. The more salinity, the more salt we leave behind in the water, the heavier this water becomes. From the coastal region, this heavy water pours into the central part of the Gulf, reaches the bottom, and outflows through Hormuz, and is replaced by fresh water, less salty water at the surface. But the speed of this recycle depends on the difference between the difference in density between the water in the Gulf and the water outside of the Gulf. The more salinity we throw into the Gulf, we leave behind in the Gulf, the heavier this water becomes, the higher the difference of density is with the Indian Ocean, and the faster this recycling goes. So in some sense, this problem is a self-correcting one. If we try to make the Gulf water saltier, we are just accelerating the circulation, the overturning circulation of the Gulf, which is, I would say, very good news. And so now I'm at the conclusions, and my conclusions after this very fast overview of several topics can only be one. We have just barely started to understand the interplay in the Gulf between wind, or in general atmospheric phenomena, the physical ocean circulation, and marine ecosystems. And with this, I stop here, and I thank you for your attention.
Thank you very much for the insightful presentation, Dr. Paparella. We have a few questions to address during our Q&A session over the next 15 minutes or so. Our first question is, what are some of the key research questions and technology solutions we should be currently working to address in order to better mitigate climate change impacts on water resources, specifically in regional hotspots like the Arabian Peninsula?
Yes, thanks for the question. So it really depends on the purpose of this mitigation. Rain enhancement is definitely part of of these activities, and if rain enhancement, in my opinion, may be extremely precious in order to replenish the natural water reservoirs and to conserve the mountain ecosystems, or in general, and the desert ecosystems that exist in the UAE and in general in the Arabian Peninsula. And I may add that are very poorly known. Not much research has been gone into studying these land ecosystems. It also, of course, is useful in order to maintain the oases that are extremely important from a cultural and also from an economical point of view in this country, date cultivations, and all that is traditional in this region. But of course, in terms of supplying water to large cities or metropolises like Abu Dhabi or Dubai, we definitely need to rely on desalination. Desalination is an absolutely strategic technology, and I should say that the Gulf countries should be proud because they have shown the world that desalination is a feasible solution. Desalination actually works, and you can sustain you can sustain the development of a country through desalination. This is absolutely amazing. In the middle of the 20th century, that wasn't clear at all. It wasn't at all clear that desalination could sustain the development of a country. And countries like the UAE have shown the world that, yes, it works. It works, and if done properly, it doesn't even have such a terrible ecological impact. In fact, it doesn't have almost any impact. If the outlet of the desalination plant is properly designed, the impacts are very reduced to a very small area. And even by emitting the brines, by releasing the brines in a closed sea, in a marginal, shallow, closed sea like the Gulf, as we have just seen, there are not going to be large-scale impacts, at least in salinity. This doesn't mean that things are easy. It's always possible to make disasters if, for example, the descalants that are used in these technologies are not chosen properly, if the piping starts to release heavy metals or other chemicals. One needs to be careful. It's not easy, but it's possible. It's possible to have a massive amount of desalinated water without any serious ecological consequence.
Thank you so much for that answer. Our second question is asking, we also know that Access has experience in using drones for environmental monitoring applications. Besides the economic and environmental benefits of potentially using drones for cloud seeding, what are the major risks and challenges involved? For example, our current drone hardware, cloud physics sensors, and autonomous control systems capable of operating in high updraft regions of precipitating clouds?
Yes, we are trying to test drone technology for a number of reasons, not just related to cloud seeding or rain enhancement. And it is a very, very interesting technology. But if we stick to the topic of rain enhancement, cloud seeding, and in general meteorological sensing, I would say that the greatest challenge right now in drone technology is not so much to operate in updraft situations. Of course, very small drones may have a problem in there, but drones come in many sizes and forms, and fixed wing drones are essentially small airplanes. They shouldn't have any serious problem except in completely extreme conditions like hurricane. But for exploring cloud formation, how rainfall is triggered, when is suitable to produce, when there are suitable conditions for rain seeding, for cloud seeding, and to perform cloud seedings, I would say that fixed wing drones are perfectly suitable. The challenge that I see personally, I'm open to debate on this, but the challenge that I see is instrument technology for sensing. For example, LiDARs are an extremely useful tool for all sorts of meteorological sensing. But meteorological LiDARs, and I'm not talking about range LiDARs that simply measure distances. I'm talking about LiDARs that measure, say, aerosols or wind shear and all these sort of things. Those LiDARs typically tend to be big and bulky, and therefore they are not suitable for being mounted on a drone. They are typically installed on the ground. Now, some companies are coming out with miniaturized LiDARs that should be suitable for atmospheric research on a drone. That is definitely a very interesting development. If we can manage to have essentially the same kind of sensors that we can use on a ground-based installation, but we can miniaturize those and put them on a drone and send the drone up into the cloud, then we will know a lot more than what we can measure a lot more than what we can measure right now.
Thank you so much for that answer, Dr. Paparilla. The third question, moving forward, what do you consider to be the most critical climate and water issue for the GCC area and wider MENA region? Perhaps you can link this to the outcomes you'd like to see from COP28 happening next year, right here in Abu Dhabi.
Yes, this is a very interesting question. And I would say that what we need is first and foremost, a change of mentality, a change of point of view. Because I have the feeling that many people, in particular, many policymakers, may have the misleading impression that it's just a matter of implementation, that the solutions are out there, and it's a matter of finding the political will and the funds to implement them. And I'm afraid that things are not so easy. In most cases, it may be that the technologies are not mature enough yet. For example, when we're talking about wind and solar energy, most people think that photovoltaic solar or wind energy from wind turbines on top of tall poles may be the solution for all energy problems. That unfortunately is not the case because those are intermittent energy sources and they need to be backed up with a base load, what they call technically a base load. So some energy source that is always available, it's always there. And we know that this doesn't work because other countries have already done the experiment. If you look at Germany, in terms of the installed wind and photovoltaic power base, it's amazing. In principle, they could power half their country almost just through wind and solar. But then you look at the emissions per capita. They are worse in Europe, worse than anybody else in Europe. Why is it so? Because their base load is carbon. So as soon as the wind slacks or a cloud passes over their photovoltaic fields, they need to put in energy that comes from very dirty sources. But those dirty sources are reliable. They are always there. So the real challenge is make sure that we invest in research to find renewable energies that are also always available, constant, that can work as a base load, that are not intermittent. And in this respect, again, I think that the UAE is perfectly positioned to be a leader in this. In Dubai, there is the Mohammed bin Rashid Al Maktoum solar park that, yes, has a lot of photovoltaic, but also has, very interesting, as a solar tower and parabolic through molten salt thermal energy accumulators. So this just means that the sunlight is used to heat up some salt, some material, which is essentially a salt, make it a very hot fluid. We're talking about many hundreds of degrees, if not thousands of degrees, which is stored underground. And that heat stays there, is not lost. It doesn't cool very quickly. It may take many, many, many days in order to cool. So now we have a reservoir of a very hot fluid, and of course, that can be contrasted with a coolant, which may just be the atmosphere. And so we can run a thermodynamic cycle. We can run a steam turbine, just what we would do with a typical thermal plant, with a typical oil or carbon plant, except that now the source of heat is not oil, is not coal, but it's the sun. And this works at night. This works at night. This works anytime. Essentially, this sort of solar technology, contrary to the photovoltaic, is like a photovoltaic plus a battery, where this molten salt works as a battery, as a heat storage. That is the smart way to go. The intermittent sources are not reliable enough, are not, in my opinion, they are not the future. They may be useful in some niche applications, but if we want to power a country, if we start thinking in terms of entire countries, they are probably not the whole picture. They may be a little piece of the puzzle, a very little piece of the puzzle, but definitely not the whole picture. We need, therefore, to invest a lot in research based on new energy sources. Another idea, which in my opinion has not been explored enough, is aeolic energy, but not aeolic energy based on poles, turbines attached to poles, but going and tapping the wind at very high altitudes. There are technologies which sound really futuristic, but prototypes are there, that use kites in order to exploit wind energy at 1 kilometer above the ground. Over there, above what is called the atmospheric boundary layer, the wind is much more steady. It doesn't slack, it doesn't go in bursts, and therefore is much more reliable for large-scale applications. So I would say that what we really should do is invest in energy research. We shouldn't think that we already have the solution and it's just a matter of implementation, because we risk to put ourselves into a dead end. Instead, if we have the courage to invest in many different technology, pursue many different lines and see which works and which doesn't work, then we will face many failures. This is inevitable. Some of these technologies will end up showing that they are not suitable for large-scale applications, but we will find some that will. And therefore, if we take the risks now, in fact, we are probably already late in taking risks. We should have started exploring these new technologies in many, many different directions already 20 years ago, if not earlier. So this is my opinion on what should be done in terms of and what should be proposed to the world. We should really propose large-scale investments in research, technological research, with the courage of exploring solutions that have not been explored yet.
Thank you so much, Dr. Paparella, for the amazing answer. I would also like to thank you again for presenting this very interesting work. This webinar is recorded and will be available on our website for those who missed the live stream. I encourage you all to attend our next webinar, which will be advertised on our channels in the near future. Have a nice rest of your day and good evening.